We left off was bottom of this page, and mostly what we have to do is it's page 3, and there's not too much, although there's some math here. We've got a bit of math to do. Oh, you can't see that. And by the time we're done with this handout, then you'll be ready to make electric guitars. But if we just jumped right into electric guitars right now, you could understand the electricity part, like how the pickup worked, but how the waves and stuff work and how you space the frets on the fingerboard, you wouldn't get that yet. All right, what do I have here? Practice, then break. Yeah, I don't know. We'll see. So period, frequency. Can't remember exactly how I defined this in past years, but period is number of waves per second. And this is sort of like, you don't have to write this part, but I'm gonna write sort of like wavelength in terms of time. So if you look at this picture down here, we've got time here, and on the previous page, this was distance. So the wavelength would be from this crest to that crest, how many meters that is. But period is like wavelength, except it's time. So if you went from here to here, that's one wavelength, and the period is the number of seconds that takes. This is kind of strange, because it sort of looks like the wave's moving this way, and you can visualize it like that, but this is not through space, this is time. So it would be like this. Somebody is standing in the water over here, and there's a wave sloshing past them, and then a little bit later there's a trough that goes past, and then there's a wave. So the water is going up and down on this person. So if you just imagine somebody standing here and getting first at time 0, they're in between. Then at about 0.1 seconds they get splashed, and then at about 0.6 seconds they get splashed again. That's what this is conveying. Sort of confusing. Frequency, I'll give an example. I think most people understand frequency. Here's one frequency. Here's another frequency. Which one was a higher frequency? The first one. So frequency is how frequent something is, or how many cycles per second, or how many waves per second. So number of waves per second. Oh.
It's the same thing?
No, it's because I screwed up. This is right. Frequency is number of waves per second. Period is just the opposite. It's the number of seconds per wave. So this is okay. This is wrong. Seconds per wave. No, let's do a little example down here. So I don't know if, yeah, what is the period of the waves below? So period would be the number of seconds per wave. So here's one full wave from there to there, from this point to this point. Or we could go from here to here, or we could go from here to here, or we could go from there to there. But no matter how we do it, about how many seconds is one, I'm just going to write one wavelength. How many seconds? 0.5. So if you're standing in the water, I'm going to draw a person standing here in the water, and imagine the waves are splashing by, and there's half a second for each wave. How many waves are going to hit them every second? 2. So what would the frequency be in waves per second? 2. And the units for this are called hertz, which is Hz. And I'm going to go back up and we'll write that up above. So they're just the opposite. Period is how many seconds a wave lasts, how many seconds for a wave to go by. And frequency is how many waves are there in each second. Symbol for frequency is just an F, and the units for frequency are HERTZ, like the car rental place. But it's abbreviated HZ. And I want to make sure it's capitalized. Do you know why some units are capitalized and some are not? Yeah. So is Hertz capitalized? Hertz is not capitalized when written out. Wait, when written out in full. However, the symbol is always capitalized. Okay, so it is capitalized because it's named after Heinrich Hertz. Okay, Heinrich. Yeah, Heinrich. It looks like Heinrich. So that is right, but maybe I should have written an H there. And the relationship between period and frequency is, I don't think I ever had you write the symbol for period, so let's do that up here. Period is T, and the units for period are seconds. So that's the period. Frequency is F. The relationship is period equals 1 over frequency. Or, guess what frequency equals? If you solve this for F. So if period is just frequency flipped over as a fraction, frequency is period flipped over as a fraction too. So it's called, do you know the word for that? T and F begins with an R. Reciprocals. Yeah, they're reciprocals of one another. So whenever frequency goes up, period goes down, because period is how many seconds the wave lasts. And if a bunch of waves are coming every second, then they don't last very long, but it's a high frequency. If the waves are coming at this rate slowly, then the period is long for each wave and the frequency is high. So we have already figured out the period of this, and I could just use this formula to calculate the frequency. Hey, look, I screwed up again, but it wasn't today. I wrote lambda equals 2 hertz. What's the symbol for frequency? F. Yeah, it should be F. All kinds of mistakes in here, but I'll get it right eventually. Wave speed. So forget that it's wave speed. Just what are the units for speed? Seconds, that's time. Meters per second. Meters per second. And there are two formulas for calculating wave speed. One we've done before, except I'm going to write it just a little bit differently. And I'm going to write it this way. I'm going to write, instead of speed, I write V. Do you remember, like, let me just give you an example problem over here. I bet you can figure it out. You've got a little car, and it goes a distance of 16 meters. And it goes that far in a time of 4 seconds. What's its average velocity if it goes 16 meters in 4 seconds? 4 meters per second. So it'll go 4 meters, then 4 meters, then 4 meters, then 4 meters. It'll add up to 16. So the formula is, for velocity, would be what? How'd you get 4, Macy? Distance over time. So this is one formula. This is the formula we've been using all year, but sometimes I've written that as displacement, delta x over delta t. Remember that? But I'm just going to write it this way. You can be flexible. So that's one. The other way to get velocity is this. If you know how long a wave is, like if I know this is 10 meters, and if I know that there are 4 of these passing me every second, then 10 meters of wave pass me every second. Well, 10 times 4. 40 meters of wave pass me every second, so the waves are going 40 meters per second. So what I just did there is you take the wavelength, and you multiply it by the frequency, the number of waves per second, and then you get velocity. So the other formula for velocity is frequency times wavelength. And this is going to be important when we're trying to figure out what's happening on a guitar string. You remember when we were in the hall? Oh, I fixed the slinky, by the way. It's okay. We were in the hall, and we had this slinky, and we were sending waves down it. They were going down and coming back. And we could send a couple of different kinds of waves. One was, this kind of wave that could go this way. So the speed of that going down the hallway, we could have calculated by like how often we went back and forth. That controlled the frequency, and then multiplied that by this distance, and that would have given us the speed. Okay, what if the speed of a wave? What is the speed of a wave if its wavelength is 5 meters and the frequency is 20 hertz? Which formula is useful here? V equals d over t, or V equals frequency times wavelength?
Second one.
Second one. So what's the speed?
20 hertz.
No. What's the frequency?
20 hertz.
20 hertz. What's the wavelength?
5.
5 meters. 20 times 5 is 100. So we can just use that formula. Frequency times wavelength, and the frequency is 20 hertz, and the wavelength is 5 meters, so we get 100 meters per second. What's the speed of a wave that travels 20 meters in 5 seconds? Does this formula help? We're given meters and seconds. So seconds is time, meters is what? Distance. It could be wavelength, but we don't have, we've got time, so we've got to use this formula. So I need V equals d over t, and the distance is 20 meters, and the time is 5 seconds, so the velocity is 4 meters per second. And now, I think we're gonna, I don't know if we're graduating to tricky ones yet. We'll hit some problems soon. Yeah, we'll do some problems soon. Actually, you know what? We should do some problems now. So these formulas, these are the formulas I just wrote. This is velocity equals distance times time, and this is velocity equals frequency times wavelength, but I just put it in the little triangle. Mr. Chase used to call his formulas good stuff, so that's why that says that. This is the speed of sound in air. This is the speed of sound in water. So see if you can do this one. How long does it take sound to travel the length of the hallway in meters? Think about it. I'm going to give you about a minute, and then I'm going to pick somebody. And if you don't know how to do it, I'll give you hints. But see if you can figure it out and walk us through what to do. So you've got two different formulas for speed. You've got the speed of sound in air and the speed of sound in water. And if somebody at one end of the hallway yells, how long does it take somebody on the other end of the hallway to hear them? All right, choosing somebody.
Prosper.
Prosper.
150 meters.
So 150 meters is the answer. Well, the question is how long?
Oh, I thought we were doing number 2.
You did number 2. Okay, we'll do number 2, and then we'll come back and do number 1. So number 2, how far away is the food? So how'd you do this? Which formula did you use?
I just, one speed of sound in water is 150 meters, 1,500 meters a second, and it took 10 seconds. So
Point one.
I just moved the decimal place over one to the left.
So were you multiplying this by that?
Yeah.
Okay, So you multiplied the speed, which is velocity, v, times the time.
Yeah.
And according to this, that gives us distance. Yeah. So you can use this formula, velocity equals distance times time. I'll just write it all out. Velocity is distance times time. You can reorganize that so that it becomes distance equals velocity. Don't let me get away with that kind of crap. Velocity equals distance over time. And that becomes distance equals velocity times time, which is, since this is in water, and that's the velocity in water, 1,500 meters per second, times the time, 0.1 seconds, equals 150 meters. And Prosper is correct. All right, so number one, I'm going to pick somebody else because everybody else probably isn't like Prosper and was actually doing number one.
Eshok.
Eshok's not here.
Max.
Max. So
50 meters divided by 340 meters per second.
so you do 50 divided by 340. Which formula is that?
V equals D over T.
This one? So let me write it out. V equals D over T. And the distance is 50 meters. And the time is...
Looking for time, so you have to use the speed.
Oh, yeah. So, oh, right. So, equals 340. So I was kind of going in a weird order. I wrote the formula like this. So I've got distance over time, and that equals velocity. So if you write it out like this, then you have to do the algebra. You multiply both sides by t, and then you divide both sides by 50. Or you could just say how long. We're looking for this one in terms of t, so t is d over v, which is 50 meters divided by 340 meters per second. And I'll just check your math on that. 0.147, 50 divided by 340. Yeah, 0.147, and the units would be what? 147 seconds. So not very long, but not insignificant. And when has anybody ever, you probably haven't, but at some point you may do timing at a track meet. So you're a timer, you're standing, here's the track, you're standing over here at the finish line, and maybe it's the 200. So the runners are starting over here and they're going to run over there. And there's somebody with a starting gun standing right there. They raise the gun, they fire. When do you start your timer? When you see the smoke or when you hear the sound? No. When you see the smoke. If you do it when you hear the sound, that time is going to take, it's probably at least 50 meters over to you. So you're going to be starting your timer 0.147 seconds late if you do that. But the speed of light is so fast that you can see the smoke almost instantaneously. So that's just a situation where the speed of sound really does matter. If you clapped your hands and there were a big wall here, and this is 50 meters away, it would take you 1.14 seconds for the sound to get there, and then 0.14 seconds for it to get back. So it'd be almost like a third of a second before you heard the echo. All right. Number 3, think about this for a little while. I want to give you a specific example. Let's say, for example, you hear the thunder 5 seconds after the flash. So, I don't know about you, but my mother misled me. We were sitting around multiple times in thunderstorms when I was really little. We'd see a flash of lightning. We'd count. Then we'd hear the thunder. We'd figure out how far away it was, and we were wrong. Okay, so let me pick somebody, and you have to explain how we do this, how we can figure out how far away the lightning strike was.
Landon.
Landon, how do we figure out the distance to the lightning strike?
We do the speed of sound in there, so 340 meters per second.
340 meters per second?
Yeah.
And what do we do with that?
Multiply it by 5 seconds.
So you're kind of using this formula. So you're getting distance equals velocity times time. Yeah, so we can do that. Distance equals velocity times time, and that distance equals the velocity of sound and air, which is 340 meters per second, times 5 seconds. And here's what I was trying to do. I didn't finish my nice drawing over here. So here's the lightning strike. So when the lightning hits, the air around it gets hot. And when you heat up gas, what does gas do? It expands really fast. And that expansion, that's like what speakers do when they push out. So it pushes out. That's what creates this sound wave. And it moves in this direction at 340 meters per second. So that would be 340 times 5, 1,700. 1,700 meters. About how many miles is that?
It's like 1.5 miles.
1.5 miles. So 400 meters is about how many miles? If you run the 400? Anybody know?
Just over.
Wasn't 4 laps on the track?
1,600 meters a mile.
Yeah, 1,600 meters is about a mile. The 1,500 in track is the closest thing we have to a mile. So this is just a little over a mile. The 400 is about a quarter of a mile. So we could get an exact conversion. Probably the easiest way is just to Google it. I'll just convert 1,700 meters to miles. 1.056 miles. So I don't know about your parents. 1.06 miles. But what my mom told me was if you count to 5 after the thunder, how far away is the lightning? What do you think? 5 miles is what she said. So it's not really that. So it's more like every second that you count is about a 0.2 miles. So if you hear the thunder and then or see the flash and you hear the thunder a second later, it's less than a quarter of a mile away. It's not 1 mile away. So all that lightning that I thought was really far off was actually really close. Let's see. Okay, so this is one that's like the number 4. This is like what you're going to have on the quiz next time. This is a tricky one. Fisherman sits on a boat in a lake and is not having very much luck, so he relaxes and watches the waves go by. He notices that the waves hit his boat in 15 seconds. Oh, sorry, 5 waves hit his boat in 15 seconds. And it takes each wave 4 seconds to travel the length of his 5-meter boat. So I'm going to draw a little picture for this. Here's so his boat's 5 meters long, and these waves that are out here, like this one and 3 others are going to splash into his boat in a time of 15 seconds. So it goes splash, 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 splash 5 times in 15 seconds. And it takes each wave 4 seconds to go from here to there. So we've got to do the frequency of the waves, the speed of the waves, the wavelength of the waves. This is kind of tough. We'll give you a little time. See if you can figure out what the frequency of the waves is. And to do frequency, you need to go back to what the definition of frequency is. Frequency is the number of waves per second. Ooh, let me give you a formula for frequency. The formula for frequency is the number of waves divided by the time for those waves to pass. It's not a very good formula. It's number of waves divided by time, basically. All right, I'll give you a little more think time, and then somebody gets to explain how to do this. Oh no, I had the randomness on 0. So what that meant is, if you were called once, you won't be called again. I'm going to switch that to 27, which means you probably won't be called again, but you might be. Okay.
Macy.
Macy, do you know what the frequency is, or can you tell me how to figure it out? So the definition of frequency is the number of waves per second. So this is sort of a formula and sort of a way of writing it, waves per second, or the number of waves divided by the time. So in here we've got 5 waves hit the boat in 15 seconds. 5 divided by 15. So the frequency is 5 waves per 15 seconds. And if you do 5 divided by 15, what's that? A third. So I'm just, should I call it a third or 0.33? 0.33. 0.33 hertz. So a third of a wave per second. Now the speed of the waves. So period of the waves would be the other way around. So if frequency is 1/3 of a wave per second, then the period, which is the number of seconds per wave, would be 3 seconds for every wave. So it takes 3 seconds. There's 3 seconds between each wave. He's got 5 every 15 seconds. So you have one, 3 seconds you got another, 3 seconds you got another. So that's the period, but we're looking for speed. Think about, there are 2 ways to get speed, and one of these we can do. All right. Landon, you've been chosen again. The 2 speed formulas are frequency times the wavelength.
Yeah.
Do we know the wavelength?
No.
No, it doesn't tell you the wavelength. In fact, that's the next question. So
we would use the
distance over time. Yeah, so we've got to use that one. We will use the frequency times wavelength formula in just a second. So with this, velocity is distance over time. Are you given a distance anywhere in the question?
5 meters.
5 meters. So how long does it take a wave to go 5 meters?
4 seconds.
4 seconds. So that's 1.2 meters per second. Then the last one, the wavelength. This 5 meters, that's the length of the boat, not the length of the waves. I haven't drawn this to scale. So this last one, I'm not going to pick anybody. I'll let people volunteer. Does anybody know how to figure out the wavelength? So for this one, you have to use the other formula, the velocity formula. The velocity is wavelength times frequency. So if I put that in the triangle, wavelength is there, frequency is there, velocity is here.
Velocity divided by frequency.
Yeah, so if we're looking for wavelength, it's the velocity divided by the frequency. And the velocity is 1.2 meters per second, and the frequency is 0.33 hertz.
3.63.
3.63?
3.63.
I trust you. Yeah, so this is basically a third. And if you divide something by a third, that's like multiplying by what? Dividing by a third is like multiplying by 3. So 1.2 times 3 is 3.6. 3.6 meters. There you go. So now I'm going to give you the practice quiz, and then if we've got some extra time, we can get into beats and standing waves and stuff like that, which are kind of fun. So this is what your quiz is going to look like next class. The number 1, number 2, number 3, number 4, they're going to be almost exactly like this. The only thing that's going to be a little different is number 5. I think I'll keep going with what I've been doing. I'm going to give you a little time to try number 1, then I'm going to pick somebody to answer number 1.
Just to practice.
Yeah. This is what the quiz is going to be like. So if you need to look back to your notes, you can look back to your notes on this. What I'm going to do before I even ask about all these things in bold, I'm going to ask somebody in just a second to tell me what a transverse wave looks like, so I can get that up here. All right.
Sylvia.
Oh, I need to kick her out of the class.
Prosper.
I want to draw a transverse wave. What do I need to draw here? What does it look like?
A line, and then go up and then down.
Like this?
Like smooth it right now.
Okay. So transverse wave is like this.
You draw a line in it.
So this is the wave itself. The line in the middle, if you look back to the notes, there's a dotted line. This is just showing the equilibrium point. So if this were the ocean, this would be what the ocean would look like when it doesn't have any waves on it. And then when you start to get waves, they look like that. But you don't have to draw the little line in the middle. It helps for one of these things. In fact, I'm gonna make little lines here, and I'm just gonna have people tell me what's what. So there's this one, and then there's this one, and there's this, and there's that. So the 4 things that you're supposed to label here are those 4 things. All right. Picking somebody. First question is this one. What's this one?
Seb.
Got out of it.
Branston.
What's this one?
Isn't that the amplitude?
Amplitude. And this one right here.
Abigail.
Abby, what's this one?
Is that like
The trough. And this one right here, the last one's going to be very easy.
Crow.
What's this one?
That's the crest.
Crest. And so this represents what?
Crow.
Wavelength. And for wavelength, if you just want to use the symbol, you could just do a lambda or write wavelength. All right. Take a second, think about this. This is a transverse wave. I want to do a longitudinal wave, and it's got to have these things in it. So what does this look like?
Max.
What's it going to look like?
It's like a box with the lines in it marking compression and rarefaction.
Yeah, except it doesn't really have to be a box. It might help if you draw it as a box. So I'm just going to draw this. And these are representing, like, this could be my compression. And then that's my, well, I guess I shouldn't say what it is. I've just given things away. You just need some squished together parts and then some spread out parts. All right. So anybody, what's this part? That's the compression. And this part? The rarefaction. And if I started here, if I started right at this point, tell me where I would complete, actually, let me do it down here. If I started here, tell me where I would complete one wavelength. Right there. That's one full cycle. So start from the end of a compression, go to the end of a compression. You could start in the middle of a compression and go to the middle of the next compression. You could, so any part, just go to the next part that's the same, and that would be a wavelength. Okay. Now number 3 says, draw 2 waves with different frequencies and periods. You can draw any kind of wave you want. One wave, one kind is easier. And we'll assume they're moving at the same speed. Label the one with the higher frequency, label the one with the higher period. So I'm going to draw them. I'll just draw them, and then you have to think about which one's got a higher frequency and which one's got a higher period. You could just assume these are water waves. And the waves are moving the same speed this way. They've got the same velocity. Okay, first question is, of these two, which one's got the higher frequency?
Max.
Max. The top one. This is higher frequency. And which one has the higher period?
Abigail.
Abby. The bottom one. So since frequency and period are reciprocal, when one goes up, the other one goes down. Sorry, I'm waiting for my lead to come through. Come on, lead. Oh no. Switching to a pen.
You might not be pressing it at the right frequency.
I might not be. That's good point. Higher period. So the way I think about this is if you're standing in the water, this top one's going to go splash, 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 splash. The bottom one's going to go splash, splash, splash. So more waves per second in this case, which is what frequency is. And this, each wave gets more seconds. The period is seconds per wave. All right. Now this next one, I want to draw another wave like these, but with a higher amplitude than either one of those. So what would that mean?
Eshok.
Not Eshok.
Landon.
Landon. I want to draw another, I could draw either of those, but I want to make the amplitude really big, bigger than each of these.
I want to draw the waves higher.
Higher, yeah, so like this. All right, so those are just the basic wave terminology questions. And now there's the one like that fisherman, except in this case it's Fred. Fred's at the beach, standing in the water, 30 meters from the shore. Fred gets splashed once every 8 seconds when the crest of a wave hits him. Ah! Okay, so the quiz.
Will not be next class.
No, it's just this.